we'll get started. Yeah, it should be about 2 hours, I think, but we'll see how we go. Alrighty, so I've just kicked off my recording and just about to share the screen. Okay, so being advanced MATLAB, I trust you all have a version of MATLAB ready to go. I'll be running in 2019B. I think there's a couple of, I think 2020A or maybe 2020B will be the latest release. But yeah, 2019B, it should all be relatively similar about now. And so hopefully you can see that MATLAB, and you've got your own version of MATLAB, and in the text-based chat, so the Remote Hardware Labs text chat, I've shared the slides there, which I'll have up on my screen as much as possible as well. But the slides are available for you to download and have a look at. Yeah, as always, feel free to yell out if any questions come up. Happy to answer them. Keep it casual. And yeah, the topics that we'll be running through will be, you may have seen some of it before, you may be relatively familiar. There's hopefully some stuff that you haven't seen or haven't done before, and yeah, that you can use. We don't focus too much on specifics in this one. It's more about developing good coding practice and finding the little bits of MATLAB that you may not be exposed to usually, but can be certainly helpful when it comes to write more advanced code. So there's a few examples interspersed through that we'll work through, and then yes, towards the end it sort of culminates. We'll do a little bit of create a little GUI using the app designer in MATLAB, which yeah, should be a bit of fun. GUIs are always fun to do and sort of know how to do because they're very, you know, hands-on and visual. You can see everything happening and they're sort of nice. But yeah, we'll work through, and yeah, just yell out if anything doesn't make sense or you need any clarification on anything, because yeah, this workshop is certainly hot off the presses. Finished about 4:30 this afternoon. All right. Yep. Mm-hmm. Pardon me? Yeah, that's right. So there's in the MUEC workshops Remote Hardware Labs text channel, which if you're in the voice chat, it's found on mine at least. It's just above the voice channel. There's a text channel. I'll see if I can. I'll just mention you up there. You might get a link or a notification of where to click. No worries. So yeah, that's where you can post any text-based questions. Discord is a little bit, yeah, it separates the voice chat and the text chats separately like that. So yeah, the slide should be up there. Okay. So yeah, I'm sure you've all used MATLAB in some capacity before. Engineering studies quite widely used. And yeah, as I said, we'll be touching on a few different topics. We're going to start off mostly discussing concepts and techniques and just adding those little tools to your own personal MATLAB toolbox to be able to solve any of those tricky problems that arise, or you know, do your MATLAB things in like an efficient and nice manner. So there's a few examples that we'll work through that come up with some interesting little problems. So the first thing that we're going to talk about is learning how to write good code in a way. So a lot of my background is certainly science and engineering, but also my day-to-day professional stuff is writing, you know, like software engineering, doing code reviews and things like that. So as scientists and engineers, we don't necessarily write the best code because we come at it from a different perspective than like software engineers or people who are studying programming specifically. So there's a few things that we want to talk about to get us writing good code that works well in any situation, not just writing code that works as a scientist to solve a particular problem, because there is a difference. There's code that works and there's code that works well. We'll try and clear up some of that stuff. So writing good code. In general, we always want to make sure we start with a plan. You should be able to start from a problem and work through in your head how to solve a problem before you write any code at all. So make sure you can conceptually solve a problem without writing any code. And if you need to use pseudocode to lay out the algorithmic structure of the solution and what you want to achieve. And if you do that, your code will be much easier to read and go back to at a later date if you're working on big projects that involves coming back and multiple, if you're sharing it with people, if you're working over it on a long time, you definitely want to be writing good code. Otherwise it can just turn into a bit of a snowballed effect of ugliness. I'm sure you've all seen this before, so we'll quickly rip through some of this stuff. Make sure you comment your code, guys. You can use single line comments, block comments with a % and a open curly brace and a closed curly brace like this. That can go across multiple lines. And hopefully you've been using sections with 2 comment symbols, 2% signs. That's really nice in MATLAB now. You can run a section of a script at a time. So in your code editor, you should be able to, this run section button, if you're using 2, do some code there, and then if you're splitting up your code with sections like this and using run section or run in advance, that can be super helpful and make things look very nice and easy to read. There's comment and uncomment buttons if you do need them to automatically indent your code, and like indent one at a time, indent or de-indent like that. So that can be useful, and it just makes your code nice. So there's no excuse for sort of badly formatted code in terms of indentation. Yep, indentation. So fundamental ethos, make sure you drill this into your heads, is don't repeat yourself. If you're copy and pasting stuff a lot, rewriting things that look very similar, you want to be thinking about, is there a better way to approach the problem? And usually loops or a function will solve the problem, but as we'll find out, loops are sort of in MATLAB, you don't actually need them a lot of the time. Certainly you can't escape them, but you can get away with not using loops, certainly, if you approach things in the right way. So scripts, MATLAB is a scripting language in that you can just run a script from top to bottom, and it should solve your problem easily in the script. So think of your script as basically taking the place of you, the user, running a command one line at a time, and it should take you, a small logical leap into the next little bit before you move on. So you don't want your top level script to be too complicated with too much stuff happening in it, and it could make sense to abstract things away down into a function or even a subscript to sort of keep it nice and neat. And you can now, I wasn't able to do this when I first started coding in MATLAB back in undergrad, which was a few years ago now, but you couldn't actually define functions within a script, which you can in MATLAB now. So make sure you use that to your advantage. It's a nice little local function that does a particular task and make things nice and succinct. So make sure you're using those to your advantage. There is a particular style guide associated with MATLAB. It's purely visual, but it can make coding in MATLAB a nice sort of familiar experience. So particularly, we like to use what's called mixed case variables for MATLAB, which is lowercase for the first word, and then if you split the, if a new word happens in your variable declaration or something like that, you start with a capital letter in the middle of it. So that's called mixed case, as opposed to cap case, which is, if I did this, would be cap case with the first capital C and then the capital midway through. Additionally, sometimes they call it a snake case, which is all lowercase and words separated with an underscore, which is particularly used in, this style is used in Python, which I think is why it got the name snake case. So you want to be using mixed caps, sorry, or mixed case in MATLAB. If you have a look at a lot of the inbuilt functions and things like that, you'll find everything is pretty much conforming to this mixed case sort of style. If you're numbering things or counting things like this, n items with that mixed case again, so you'll see this a lot, can be nice, and it's sort of, as humans, as soon as we see this, we should be able to think, okay, this is telling us what the number of items is, or the number of cars, so make sure you're using that for counting. Logical things, so if something is true or false, start it with is, so is successful, but definitely don't use is not successful, because that sort of flips everything upside down and can be hard when you start using it in if statements and things like that. So you just want to negate is successful if you're doing that. So yeah, that's handy. Starting things with is, naturally you then start thinking about if something is true or false. So is successful, true, false. Defining constants, you can do that all in caps, like that. Oftentimes like a big constant, we don't do that too much in MATLAB. Can be like if you're defining a constant variable, can sort of help things stand out. But yeah, all caps can, it's reminiscent of global variables really, although we don't use globals that much either. Loop variables, so if you're using things in a loop, I, j, and k preferred. So you'd set it up like this for I car equals 1 to n cars, like this, or m, n, and r, or idx are often quite common for loop variables as well. The trouble is, then I actually has a special meaning in MATLAB, being the square root of -1. So that's why we like to use 1i like this for the square root of -1, because you can imagine if I look at I squared without having anything else in MATLAB, I squared equals -1, but if you imagine if I'm looping over something and my I is my index variable, and I finishes up at 5 or something like that, then I do I squared again, all of a sudden my meaning of I has changed. But 1i will always remain as the square root of -1. So if you're using complex numbers, use 1i, or I think 1j as well works. Yep, so for engineers, j for that complex variable. So make sure you do that. And generally for setting out, make sure you include the white space around operators. So a space equals space b space plus space c. Looks a lot nicer than when it's all squished together like this. And there's a link there for a useful style guide cheat sheet for MATLAB. But if you do all these things, you're going to start getting familiar with the way that MATLAB code looks, and you can sort of pick out what the good parts and the bad parts of MATLAB code when things conform to a style guide nice and easily. So try and follow this sort of convention if you haven't been already. It'll make a huge difference to not necessarily the functionality of your code, but the neatness of your code, and the way that it looks, and how easy it is to sort of read and view other people's code if you're respecting that style guide. Okay, so that's the sort of the flair of writing it. Let's have a look at writing efficient code, or nicely performant code. So not so much useful for doing little tasks, but when you start writing bigger programs in MATLAB, making sure you're doing things efficiently can actually be quite useful and important because the difference between waiting, an hour for your code to run versus waiting 2 minutes for your code to run can be massive if you're doing tasks over and over again. So we want to make sure you're writing the most efficient code possible. And yeah, starting with simple little examples, starting doing it in your assignments will be good practice for when it comes time to writing big stuff. But I guess for your day-to-day things, the difference between something running in half a second and something running in 2 seconds isn't that big. But when it comes time for those big projects, it's really going to pay off to know how to write efficient code. So we'll have a look at some things that. And the first step towards that is knowing what data types are available. Okay, so numerical data types will be the stuff that you work with mostly. So when it comes down to it, there's some big difference between the types and the ways that numbers are represented. So we'll have a quick look at some of them. So double is a double precision floating point. And it takes up 64 bits of memory per double number. And that's the default type for MATLAB. We've also got single precision, which is 32 bits, which is so half the size of a double. If you're dealing with integers, you've got uint 8, 16, 32, and 64, which have those corresponding amount of bits to represent them, and so uint for unsigned integers and int for signed integers, which can have negative numbers as well. So depending on what you're dealing with, double will get you through most of the way, but when you're starting to think about efficient and performant code, thinking about exactly how you want to represent your numbers can be quite important. So we'll quickly punch this in just to sort of see what the difference is. So we're going to create a random array of double precision and a random array of single precision and see how much memory they use. So d equals rand 1000, and to specify the data type, you just include the string double like that. And we'll do a single one. Okay, so you can see in my workspace I've now got 1000 by 1000 of double and 1000 by 1000 of single as well. And typing whos will let you know how many, what's in your workspace and what type they are. So you can see D is 1000 by 1000 double, and here's the amount of bytes that it's taking up, and there's the amount of bytes that my single precision is taking up. So this is, if you're doing a massive computation and you've only got a limit, these days it's not so bad because computers have a decent amount of RAM to work with. But if you're dealing with huge arrays or matrices or something like that, you can quickly actually run out of RAM and run out of memory when you're actually storing these big arrays. So choosing the type can become quite important because it will severely impact the performance of your code if you run out of RAM and potentially cause some awkward things to happen. So there's single and double and a cat. Hello. Yes, I know, it's your dinner time. Off, please. Sorry about that. Okie dokie. So data types for numericals, there's your basic ones. Some non-numeric data types. We've got MATLAB logicals, which are trues and false, and they appear as zeros and ones in your code. They actually take 8 bits of memory to store a single logical value. And you might think, why does a single bit, because a logical bit could be 0, 1, true or false, just one single bit of memory should be enough to do that, but MATLAB actually uses 8 bits to store a single true or false value. So you might ask, why does it use 8 bits? And it's actually the way that computer architecture is these days. It's actually more performant to access from your RAM a block of a byte or 8 bits at a time. So that's why it's we use that for a logical, is 8 bits per value. There's categorical arrays. I have never used them that much, to be honest. Chars with single quotes. This used to be the only way you could store like a string value. But now there's actual strings or a string array, which is initialized with double quotes like this. And generally we like to use the strings these days. The use of chars, you don't really need them that much, but you may need to use them. Have a look at the difference. Let's have a look at this one. So we can put in a character array. That's right. Instead of doing that, just give me 1 second. We can explore the difference by, just pull up my source code here so I can access the thing. And if you can't be bothered typing it out as well, there it is in the text chat. Not that one, I've posted the wrong one. Sorry, I want this one. Okay, and you can have a look what happens when we've got those defined now. So a character array, all the values and rows, they must be the same length. So it's basically like a matrix, but with characters in them. So it needs to be uniform in size. So you can see like wire has to be padded with spaces for this to be a valid character array, which is a 3 by 12. So it's 12 characters wide and 3 downwards. Strings, my S array, doesn't have that same constraint on it. Each of the values in there can be different, and what happens when I try and access different parts of them. So the first element of the character array is W for wire, and the first element of my string array is the whole string wire, and that can be a bit of a difference there. And the same way if you're doing like slicing on those. So if I slice down the second column of that, that's I, A, and O. But if I try and do the same thing with my string array, we get an error there because it's fundamentally different at its core, the way that we access those things and the way that they're represented. So stick to string arrays these days most of the time. And there's a bunch of generic data containers that can store, I guess, random sorts of things or different types of data, whatever we need. Cells are quite common. I use cells quite a bit, and they come, like a lot of inbuilt functions will return cell arrays. So if you haven't used cell arrays, we'll go through a quick example with those. Structures are common as sort of like an object, but they don't quite give as much useful like methods as generic objects. But structures are quite popular for storing named fields, and you've probably come across them before, even if you haven't quite known what they are. And tables as well, although I don't really use tables that much, haven't found them to be that useful. And of course, MATLAB is an object-oriented programming language, so you can create your own generic classes for, sort of that low-level object interaction. But usually, if you're just storing data, structures can get away with that. So we'll do a quick example with a cell array. So a cell array can be used to, we're going to use it to store transfer function objects. So if you're doing engineering, maybe you've come across transfer functions before. Or like control systems or any type of signal processing. We're going to store those in a cell array. We're going to use something called a cell function to plot the Bode diagrams of each of these transfer functions. Without looping over them. So if you imagine you had a bunch of transfer functions and you wanted to plot the Bode diagram, you might loop and plot for each one. We can actually do that without using a loop. And yeah, we'll quickly go through how to do that. So I will post up that definition to save you writing it out. Which is there. So you can jump into the text chat and copy that over. Just going to clear out my workspace. And I'll just create a new little script. So you're going to want to do this in a script. Paste that in. Quickly save that to cell function example. Okay, so I run this, and this creates the variable TFS, which is a 1x3 cell array. So if you have a look at that in the TFS, it's a 1x3 cell array, and each of the elements has a 1x1 transfer function object in it. So if we wanted to manipulate this cell array and do things with it, one way to be would start by, maybe the old way, or sometimes you can't get away without doing it, but you might do something like for I equals 1 to lang TFS. You might start doing something like this. You might do like Bode TFS and then access the ith element of that. We create a new figure and then we hold on. This might be the old way that you would create the Bode plots for all of those transfer functions in one go. So looping over it and applying a function to a particular element of that. So instead of doing that, we're going to use something called a cell function, and a cell function operates on a cell array, and it will perform an action, or it will run a function on each of the elements of the cell array. Basically what we're doing here. So as always, a good place to start, right, if you're not sure, is pull up the documentation for a particular function or something you're trying to do. So help cell fun will get you the documentation for this cell function, and then yeah, you can have a read of that. But basically the first argument that we give it is a function handle, and the second one is the cell array that we want to apply each of the functions to. So if we do cell fun, the function that we're going to apply to it, the function handle, is we use @ and then Bode because it's in the base workspace. and then the cell array is TFS, like this. Okay, so now running this, we get the exact same behavior that we did last time, just in one line basically. So we don't need to loop over anything at all in our base code, and it's going to apply that function to the contents of that array. So we're using transfer function objects here. They're not necessarily, there's no reason why they have to be transfer function. They can be anything that you like. That's the beauty of cell arrays. They can hold generic data, anything that you like. So I think then we want to write a custom function to show the Nyquist plots and print the location of the poles, so that's the roots of the denominator of the transfer function, to the command line. So if we had one transfer function, usually we'd just call the Nyquist plot like this. So for example, this will be the Nyquist plot for the first create a new figure first and then do that. So here is the Nyquist diagram for that first transfer function, which was 1 over s. And then this is how we'd call the Nyquist plot. If I want to do it the same way that I did in my script, we might try and do that. Instead of Bode diagram, I might go Nyquist, see what happens. And it actually works this time. It wasn't working for me before. I'll have to modify my example a little bit. So that can get the Nyquist plot for all of my transfer functions in one go. The other thing that you can do is call a custom function. So I'm going to define a function below. Function custom function, I'll just call it something like that, or let's call it something better, plot Nyquist and display roots, something like that. And the object that it's going to take is just going to be a transfer function object by itself. And then, oh, wind just picked up, getting pretty ugly out there. And then the thing that we want to do to that, so this is what we're going to do when we apply to a particular object. So each one of these transfer functions will get called one at a time when I do this. So first thing that I want to do is Nyquist of tf funct. And then the other thing that I wanted to do was, what did I say it was? It was, oh, lights are flickering here. Print the location of the poles to the command line. So the poles are the roots of the denominator. So if you know about the transfer function object, there's a property of that transfer function called denominator, which has the denominator coefficients in there. So the ones that I've defined up here, we can actually recover these. And it comes as a cell, so I just need to unwrap that cell. And then if I want to find the roots, I use the roots function like such. Okay, so here's the custom function that I'm defining. Now, how do I apply it using this cell function? So that I need to put the @ symbol to make it a function handle, and then I just give it the name of my custom function that I've written down here. So the cell function is going to apply this custom function to every single element of this cell array, like this. So if I run that, we get our Nope, I just got a message saying that I've been disconnected. Is that correct? Do I still have connection? Am I still streaming? Have you broken? Up. Okay. All right. So if I haven't missed anything, and let me know if I have, we're just about to apply a custom function to my cell array. I've defined my custom function here, and I've given it the function handle of the custom function that I want to apply. And when I run that, I think I need to do disappear to display that to the command line. If I run that now, it is giving me the Nyquist diagram for each of my transfer functions, and as well to my output, it is displaying the roots of the denominator of my transfer function. So that can be a nice succinct way to sort of manipulate things that exist in cell arrays by using this cell function or cell fun, which will apply a custom function or apply a function to individual elements of that cell array, which is quite nice. I've used that one a fair bit before in different, various different ways. All right. Of course, you want to try and vectorize your code where you can. MATLAB's very good at having nice vectorized code. We use it all the time. We don't even think about it. So things like when we call sign of t and t is an array, that's an example of vectorized code. There's no looping involved. We don't need to loop over individual elements and apply the sign function. It just naturally works with a vector. We have computations over a particular array dimension, like sums, differences, means. Probably use those a lot. Logical indexing is something that is very nice. So this would access all elements of A, where A is less than or equal to 2. So we don't need to use any loops there, or types of logical reductions where like any and all. So these will return true or false depending on the contents of a logical array that goes into them. So we'll see some examples of these, I think, in a second. Pre-allocation, certainly if you do need to use a loop, if you can't get away with vectorization, make sure you pre-allocate your code, pre-allocate your results array before running the loop. Hello. You want to make sure, like, don't do this. Don't just change, don't just append to the y. Make sure if you know how many you need, initialize that y array and then allocate to it. So you will be able to see the difference between these two when we start looking at speeds and how efficient things are. So pre-allocate like that. A couple of ways to examine the performance of your code. So tick and tock. sort of work together. Tick will turn on a timer and tock will stop the timer and display the output. So you can have a look at how long this will take. If we did tick a equals round 1,000 and a inv equals, okay. If I run that, it tells me that the elapsed time, how long it takes, is 0.115909 seconds. So you can use that to time your code and get an idea of how long things are taking to run. The other way is to run and time your code using this button for your editor here, and that will sort of, you don't need to be as specific as tick and tock like this. You can see the detailed timing information. So I'm going to post up this code, and definitely, or maybe if you want to type it out yourself, so you can get a feeling for what pre-allocation looks and feels like, and vectorization, but I'll probably post it up and we'll just have a look at just how different these things are when we actually come to run them. Okay, so just pull up that code for you and paste it in. Okay, so make sure you include the clear all as well. It's quite important for this example because it releases those variables from memory. So usually, I mean, we can just run this code like normal and that will do what we usually want it to do. It'll put these variables in the workspace, but really what we want to do is run and time. So if we hit the run and time button, we'll see what happens. So you get this profiler window come up and tells you some statistics about it. So if you click on the script name that comes up, we'll get some more detailed information there about exactly what is happening. And we can see it breaks it down by line number, exactly how many calls or how many times that line number gets run, how long it's taking, and what sort of percentage of time things are taking in that. So line 5, that was our loop without any pre-allocation. So this is the sort of worst way to do it, and we can see in terms of timing, it certainly is the worst way to do it, because every time we hit that, that's 50% of our total script running time is done by that calculation, and particularly assigning it to this loop variable and sort of incrementing that each time. When we pre-allocate, that's also taking a little bit of time. So we've pre-allocated this loop variable and then the results, and then when we write to it, it's already there. We don't need to find any new memory for it, which is actually what's happening under the hood. And then we assign to it. But that is, it's taking significantly less time compared to the non-pre-allocated, but it's still quite a bit of time. The absolute best way to perform this is using how we would probably do it naturally, is using the vectorized version of this code, which is just saying, 2x squared plus 3, using this x variable that we've already predefined there, and using, MATLAB's inbuilt vectorized code for mathematical operations, which is very, very quick because it's not, it's not even appearing on our timing diagram here. It's part of this all other lines there. It's very, very quick compared to each of these ways. So definitely use vectorization when you can. There's, certainly the best way to go. And if you can use vectorized, you definitely want to. Okay, what do I do next? Breakpoints. If you're doing some debugging, you can use breakpoints. I don't use them that often, to be honest, but it will pause your code execution and allow you to inspect the state of each variable, and then you can continue execution until the next breakpoint is reached. So you add a breakpoint by, here's our breakpoints button here. So if I wanted to say add a breakpoint to this line here, I can click on set breakpoint, and you can see this little red dot comes up on the left hand side. And then when I run, I think, yep, so you get this little paused in debugger message, which means that we've hit this breakpoint. So you can see like that. So that means we've come through this loop once and we've hit the breakpoint and we've stopped. So you can see in my workspace, index is 1, which is the first point of this loop. And then you can continue your code until the next breakpoint. So I hit continue and index is 2, hit continue, index is 3. So you can just keep incrementing those through your loops. We don't want to do it for every single one of these, but you can inspect the state of the variables, you can have access to them, you can see what's going on. So if if your code's failing at a certain point in the loop, you might want to consider using a breakpoint, and you can sort of jump in and see exactly what's happening in there. And you can just quit debugging. And yeah, we'll go back to running your code normally. So breakpoints can be useful if the situation calls for it. Okay, we've got a little bit of an exercise. I will do probably this first exercise, and then there's one straight after, which is sort of putting all these different things together. We'll do this one together, and then I'll leave you for the second exercise. Then we'll have a bit of a break, and then we'll come back and we'll finish off the workshop. Yeah, because probably we're just about at our limit. So linear regression. This is just using vectorized codes, practical example. So consider a set of n experimental measurements consisting of x's, y's, and delta y's. So this is a uncertainty in that y value. So it's an independent variable, and then we might measure a particular variable, another variable with some inherent uncertainty around it. And a weighted least squares regression is defined by the relations which are found on the following page, and it's going to give us a slope m and an intercept c such that y equals mx plus c is the best fit for the data given. And it's weighted because points with a smaller uncertainty in y are going to influence the fit more strongly. So you can imagine if a data point has a very big variation, we may not want that to influence our linear fit, because there may be something wrong with the measurement. It could be an outlier or something like that. Something where it's got a very small uncertainty, we might like our linear fit to conform to that point more. So here's our task, is write a MATLAB function that takes 3 vectors as input, x, y, and delta y, and returns the computed values of m, c, and their associated uncertainties, delta m and delta c. And here's the different relations, mathematical relations that give that. So we can do this all without looping over anything at all, even though the summations indicate that we might need to. But MATLAB, luckily, we can just vectorize our code quite nicely. So we'll jump in, we'll start to write this one, and then yeah, hopefully you come up with the same answer. So certainly you should be trying this yourself as well while I work along. So just flip that over to this page. Okay, so I want to create a new function, and often if you use the function template, so by going new and drop down to function, that will give you a nice little function stub here to build your function off a little bit easier rather than starting exactly from scratch. So you've got some predefined document strings, inputs and outputs. So we'll use this. Sometimes you don't need to, but it's a good place to start if you don't know what you're doing. So I said I wanted 3 input arguments, x, y, and delta y. So we'll call those something similar, x, comma, y, comma, delta y, like that. My function name, I'm going to call it weighted linear regression. And my output arguments, I wanted to be m, c, delta m, and delta c. Okay. And just filling out the document string. Weighted linear regression. Calculate the line of best fit. And you can put as detailed comments in here as you need to. We'll just leave it at that for now. So get rid of these default ones. Okay, so now we can start writing our function, which is based on these. So the first one, let's create this vector of weights, which is just 1 on the error squared. And MATLAB, we can do that pretty nicely. Call it W equals 1 on, what's our variable? It's delta Y. Autocomplete doesn't help. And we square each element in delta Y. Okay, so this W is going to give us a vector, which is each of the elements of delta Y squared, which is exactly what we want. Okay, what else do we have? Eventually we want to get to M and C, but I need to do some intermediate variables next, so we can do D, which is defined by this, the sum of each individual weight multiplied by x minus x bar. Actually, I need to do x bar first. This just uses the weights and the individual x's, so we'll do x bar. We'll call it x bar like that, using our mixed case sort of style guide, equals, and we just use the inbuilt sum function for this one. So it's sum of W element-wise multiplication by x divided by each of the weights, and I just need to use element-wise divide divided by W. So this should give me x bar. Similar for y bar, we'll do that now. W element-wise multiplication by y divided by W. Okay, that should be good. And now I can get D, my big capital D. So D equals the sum of, and element-wise, weights multiplied by x minus x bar. Okay, so that should give me D being a single value because it's summing up all the different values in this array here. And then I can also do lowercase d, di maybe, equals y minus, oh, I can't do that one just yet because I need an m. So now that I've got d, I can do m and c. So m equals 1 on d multiplied by the sum of W multiplied by x minus x bar multiplied by y. So something like that should get us there for M. C equals y bar minus m by x bar like so. So that should be a single value. And then I can then do d y minus m minus c, fixing my style up, something like that. And then delta m and delta c. That's what I call them, yep. Delta m equals 1 on d and then multiplied by the sum of x minus x bar multiplied by y. And, oh, that was m. I want delta m, don't I? Sum of, let's start again. 1 on d multiplied by the sum of w element-wise multiplication of d squared, and all that divided by n being the length of, we can just use any of them. I might actually define that earlier. Let's call it n minus 2. And up here I'll just define m as being equal to length of x. Can be any of them, x, y, or delta y. So that should be delta m, and I just need to take the square root of that now, because my definition is given as the square. And finally, delta c equals okay, 1 divided by the sum of my weights. That's a bit ugly. I'll just get rid of one of those brackets. Sometimes it's good to be clear with your bracketing. Other times you don't necessarily need it. So 1 on the sum plus x bar squared divided by d. So that should just be all scalar values, and then multiplied by, and I think I've used that one just up here, it's this term. Yep, and again I need to take the square root of that, like such. Okay. So that should give me everything. Just look at my output. Okay, so yep, I've I'll call that D. That should keep it happier because I've used D below. I've got an uppercase and a lowercase. Sometimes you want to be careful about mixing upper and lowercase variables, depending on whether your language is case sensitive or not. But yeah, that should be fine in this case. The only thing that's missing, or I'm really noticing that's missing, is comments. So you want to comment your code. You know, weights. These are technically the weighted average. That's why they're called bars. Number of data points. The D's are something akin to the residuals, and then slopes and intercepts. So just always be commenting because it's good practice, and then uncertainties. And then yeah, as long as we're returning those values in our function, this should be all good. So no loops required. We're just leveraging all of the inbuilt functions, element-wise multiplication, and things like that, the sums, There's probably even, if we wanted to, there's probably even something resembling a weighted average inbuilt function that we could use, but this will do for now. Okay, and when we save that, just remember with your, when MATLAB functions, the file name should be the same as the function name. Okay, so now I've got this function called weighted linear regression that I can use. And then we can pop up, I've got a example data set here that I will post up, and you can use that to test your code. Okay, so copy that in. So you can use the error bar function to plot x, y, and delta y. You can do hold on, and then we can plot the values of x, and then we'll use this weighted linear regression. We will return let's get those values back. Let's get m, c, dm, and dc back. Of x, y, and delta y. And we can do plot x versus m times x plus c. And we should be able to see what's going on with our linear fit. Let's see if this runs. Yeah, I thought I might need to. We'll just need to do a new script that has all this stuff in here. Okay, so you've got to do this in a separate script, and then you can call that function like that. So if I run that now, nope. Okay, so I've got one extra thing here. I just need to go back in and go to line 25 and just do element-wise power there. That should be a little bit better. Okay, close all my plots. What's going on? Save this somewhere. Okay, and that doesn't quite look right. So I will have a look at that. I think what we might do, we make a break. I've probably made had a little mistake in there somewhere. I'll have a little bit of a break, and we'll be back to finish off the workshop and quickly do the next little bit. There's not too much to go. Mostly a little bit of talking, and then I want to get to the GUI stuff at the end. But I'll be back in. I'll fix this example up. We'll do the next example, and then we'll do a bit of yeah, just finish the rest off. So thanks for joining. I'll be back in probably 5 to 10 minutes or so, and yeah, we'll see you then. Thanks a lot. Hi, welcome back. Just having a look to see where I went wrong in this one. I found one thing. I put the one thing was wrong. It should be the x bar of the sum of the weights actually, rather than just the weights, which was one thing wrong. Just making sure, see if there's anything else wrong. If there's, looking at what I prepared earlier. Yes.
I'd just like to ask again, where did you find the profiler to check the running time?
So it's under the editor button, the editor tab, and then run and time. This button here is the one you're looking for. That's got the profiler. Yeah, no worries. Okay. D x minus x bar squared. That could be the issue. Let me have a look. Yep, I think I've just copied the wrong thing. Yep. In my haste, I've just messed up all these definitions. So that should be x minus x bar squared. And did I get anything else wrong? Okay, let's see if that looks any better. There we go, that looks a lot nicer. Okay, so I will amend that, but if you're following along, there was two things to change, or three things actually. In x bar and y bar, it should be the sum of the weights times x divided by the sum of the weights. Same with y bar, and then also in D, the residuals, it's the sum of the weights multiplied by x minus x bar squared. So that's missing in the definition from the slides. I just miscopied them over. I will update those and redistribute. But yeah, using that data and the error bar function, which is a nice little built-in MATLAB function, you can plot, so the data is in blue with the error bars shown in the vertical direction, and yeah, there's our line of best fit. And you can see the, if you want to play around with it a little bit more, you can change the delta y's on some of them, and you should see that anything that with a really tight error bound on it will contribute to that fit a lot more. And the ones with a broader, wider error bars on them will not influence the fit so much. So this is easy to code, but actually quite useful. I use it tons in my undergrad. This weighted linear regression to get a best fit, particularly the error bars on the slope and the intercept are quite useful as well. Okay, so that was that one. Here's another one, and I'll probably, just based on time, I'll probably just show my solution to this one. And yeah, we can discuss what's wrong with it generally as well. So a code refactor. A friend has asked for some feedback on the code that they've written. They want to find the experimental probability that from 1 million trials, the sum of 3 dice rolls is greater than or equal to 12. So we add up all the numbers that appear on 3 dice, and there's our total. We want to find the experimental probability that's greater than or equal to 12. We also need to find which rolls and which 2 18s appear in a row. So here's the code that they wrote. Any comments that we want to make on this code that they've written? Does it look like code that I've written before? Maybe, from a while ago. Thankfully, I don't really write code too much like this before anymore. If it's code that if it looks like code that you write at the moment, then you're in the right place, I guess, because there's certainly a few better ways we can do this. So first thing that I would comment on is lack of indentation. Certainly, at the very least, we want to be indenting the code. Looks like there's a lot of for loops happening There's no comments happening. So these are all things that we can improve on. So first thing that we might do is just copy this code in and see what the indentation, the automatic indentation does to it, and go from there. I should have a copy here. Yep, so here's that code. If I hit it with MATLAB's auto indentation, I just highlight and click on this one, Smart Indentation, or Command I, or Control I, that will indent, give us a little bit better of an idea of what's going on. So our friend is looping 1,000,000 times. They are doing 3 dice rolls like this. Rand I, so a random integer from 1 to 6 is what this will give us. Save that into dice 1, 2, and 3 variables. We add them together, and then we store them into the results array. So we do that, we roll our dice as we get the sum. And then he's defining a count variable, looping 1,000,000 times again over each of the results. So we get the result, we store it in a variable called trial. We say if trial is greater than or equal to 12, we're going to add 1 to our count. So that's pretty straightforward too. And then we're displaying in a proportion. This is the experimental probability. So the count divided by 1,000,000, which is how many trials that we're doing. So this is displaying the probability. And then to find the rolls where we roll 2 consecutive 18s, he's looping over the 1,000,000 rolls, or 1,000,000 minus 1, and then we're getting the trial from that roll, and then the next trial from the one after it, and we're seeing if this trial is 18 and the next trial is 18, then we're going to put in the indices, put in the I value into the indices array. So this is the appending to that indices array. So let's run and time this code, and I'll copy this over again for you to the text channel if you want to run it yourself. And we'll run and time, we'll just see what our code profiler is doing, what's hitting us badly. So it took 4 seconds to run. You can see a lot of time is spent in this defining the random variable, a lot of time spent summing it up, and then yeah, that's obviously the bulk of the time because everything's gone into this other lines here, but there's certainly a few things that we can do to tidy that up. So any ideas what we'd want to do differently with this before I show the solution? Anything you can see based on what we learnt so far that we can immediately fix up on? Where's my good solution? Yep. Okay, so here is the sort of one of the good solutions that I wrote. You know, there may be more than one, but this is the best, well, one of the better ways to do it. Certainly better than the code that our friend had written. When we're starting our scripts, it's nice to define sort of variables up the top. They could be constants as well if we wanted to use the style guide, but it doesn't really matter in MATLAB. Certainly the number of dice that we want to roll, 3, is not particularly clear in the old one, and they're hard coded in as individual variables, which isn't great. The number of faces on the die, if we wanted to, you know, do this again with different styles of dice, we could do that. The number of trials is now defined a bit nicer if we needed to change that. You know, if that changed, we immediately have access. Think about all the points in this code where that appears and how many times we would need to change that if we wanted to do it for a different amount of trials. And then also, perhaps if we wanted to change the threshold for which we were calculating that experimental probability. So try and define parameters first up, nice and clear. They're all in one spot. If we wanted to change any of those, we can. And you might want to comment those a little bit more detailed if you want to. So in your script, the next thing that should happen is the sort of computation and the outputs. So we're doing the rolling the dice, and in this, I'm doing an intermediate result from individual rolls. So rand I will, the first argument is the, between 1 and n faces is the random number. And then the other two will actually create an array of random variables. So if I create an array of, in this case, 3 by a million, that's going to have each individual dice rolls stored in this result. And then what I can do is sum those up over the first axis. So if I just put a breakpoint here and run my code, let's see what happens. So I've stopped here. Actually, I need the next line. Just add in another breakpoint and continue to the next breakpoint. If I have a look at result now, it's a 3 by a million. So 3 is in the first axis and a million is in the second axis. So if I sum over the first axis, that's going to combine each of those individual dice rolls by summing them up, and then it's going to be stored in my result array. So now, after I've done that, result is a 1 by a million array, okay, with my sum of 3 dice rolls stored in each of those entries. Okay, and then once I run that, I can do my count. I use logical indexing. I want to find my result array where it's greater than or equal to the sum threshold. So I don't need to use any loops here. I can just use logical indexing. And this array here, when I do logical indexing like this, result greater than or equal to sum threshold, that's an array of ones and zeros, or logical. So it's 0 when my sum is less than, and it's 1 when my sum is greater than or equal to. And then by summing that up, it sums up all the ones and all the zeros. Obviously zeros don't count, so by summing up all the trues or all the ones, I then get my count value in a nice simple one-line fashion. So that's a nice way to do that. And then we output the proportion using a nice fprintf statement with nicely formatted values for the, parameterized by the number of rolls and which threshold I'm using. To find the consecutive 18s, so this is a little nice one. So we don't need to loop and get the trial and the next trial for this one either. Actually, the way that I thought about it was I find all the points where my array is equal to 18, or my array, almost every value in my array, just up to the end, one before the end. We'll see why in a second. So that is a logical array. It's going to have zeros where I haven't rolled an 18 and a 1 where I have rolled an 18. And then what I do for the next one is I use diff. And then, so difference calculates the consecutive difference. So if I just do diff of that result, it's calculating, so like the second entry minus the first entry and the third entry minus the second entry. So if I roll a consecutive number, that's when it's going to come up with a 0. So 2 consecutive numbers in a row are going to come up with a difference of 0. So I'm using that, and then I'm using logical AND between those two arrays that I've found. If I do where is my rolls 18 and where is the difference 0, that's going to give me where I've rolled an 18 and the next one is an 18. So this one is going to give me lots of zeros, but every now and then there's going to be a 1 in there where that condition is true. And then I use the find function. And the find is going to return index values where these conditions work out to be true. So I can paste that in and see there's a few numbers in there, and these are the roll numbers where I've rolled 2 consecutive 18s in a row. So no loops needed there, and quite a nice little compact way to do it. This would probably do with some commenting to be sort of nice and thorough and be really clear about what's happening, and I will just store that in that value there. So a little bit of abstract thinking to get that one out, but I think this code is a lot nicer to look at, and computationally, if we run and time that, we should see it's run in much less time compared to the other one, so only 0.66 seconds compared to the 4 seconds or so of the other one. So a lot quicker, a lot more computationally efficient to run this code, so overall a better solution. And yeah, most of the time spent here is actually defining that random array, which makes a bit of sense. There's very little time taken in the computation. Great, so any questions there? Otherwise we'll keep motoring on. Excellent. Okay, I'm going to brush over a little bit of this stuff. I don't do too much here, but often creating nice data visualizations is understanding the hierarchy that MATLAB uses to store its graphics objects. So what's actually happening when we call something like plot X and Y? And essentially it creates a structure like this. So root is our base MATLAB application, and then we've got figures, which you should be comfortable with creating and viewing, but figures, and then each contain things like axes, annotations, illustrations, any user interface elements, and primitive chart objects, so things like lines and things like that. We'll have a quick little look actually. I'll show one example, just a slightly different way. So the way that you might be used to changing properties of plots is to use like grid on, grid off, like title, and then you give it a string and things like that. There's other ways you can do it. So I'll just go clear all, so you'll see, close these off. Sweet. So I'll just create a quick plot. And oh, there it is, there's my plot. So GCF is an inbuilt function for get current figure. So whatever your current figure is, it will store that into my fig variable, and then we can have a look at the children of figure is an axes. So that's one level of the hierarchy below. A figure can have multiple axes if you've got like subplots and stuff happening, but in this case my figure has one simple axis like this. And then similarly you can store that axis in using GCA, get current axes, or alternatively I could go fig.children, because that's my only child, will be stored in our axes. So then I can have a look at the children of axes. And we've got this thing called a 5x1 line array, and that is each of my 5 lines that have been plotted here. So they're actually stored as children of these axes object. Let's have a look at the first element, so I'll just call this lines. Okay, so now I've got lines, which is this 5x1 line array. Let's have a look at the first element of that and see what it is. So it's the first element of my lines array is a line, and it has all these properties. So here is our usual things that we're used to seeing, like markers, line styles, the data. We can see all the properties. There's a lot of properties on that line, and we have access to changing each of them. So if I do something like what I'll do, let me just drag that across and bring up my figure so we can see. Let's say I wanted to change the property of the first line. Well, I've accessed that first line somehow, or that could be equally done by axes. I could look at the children. It's give me my lines, and then I can look at the first element of that, and then I can do, let's maybe change the line width. And let's change that to be 10 or something like that. Did that work? Let me try lines 1. I think that worked. Oh yeah, there we go. Bit slow for some reason. So you can change the line properties by just doing from the command line like so. If I wanted to change the marker style, you can just access properties directly in the same way that we'd usually define those. Maybe I do that on like the third line that was plotted or something like that. Is it just marker? Yep. So now on my plot you can see that the third line, which happened to be the yellow one, has now got circles as the marker. I could maybe change the marker size to be something that we can see. Yep, so it's made those a bit bigger. So it's a slightly different way of interacting with properties of a plot. Can be useful depending on what you're doing. It's very useful to know how to do it if you ever need to. So yeah, probably a different way, and there's plenty of stuff that you can do once you get into that object-oriented style of sort of coding, which is where some of the real power comes from. Right. All right, we're almost there. So toolboxes, we'll quickly chat about those. If you weren't sure, you can see what toolboxes that you have installed by going to Home and then Add-ons and then Manage Add-ons. If you're on the student license, you should be able to have access to a bunch of different toolboxes which are inbuilt, or you at least have access to download them without paying any money, which is nice. But yeah, they oftentimes, like signal processing, Simulink is actually a toolbox, and then all this other stuff, depending on what you're doing and what you're needing, you might have different toolboxes. Additionally, the MATLAB file exchange is a good place to go for the community toolboxes and functions and whatnot. There can be a lot of good stuff up in there, so there's a link there to the file exchange. And yeah, there's plenty of stuff up there of varying quality. Some of it's great, some of it's not so good, so just approach it with caution. But that's the community stuff. Okay, and then I want to finish up with, we're just going to create a simple little GUI app, which is quite fun. If you haven't done any GUI programming before, it will seem a little bit daunting. And there may not be that much use for it in the day-to-day, but again, it's good to know. So some fundamentals are a GUI app is an object with a number of child properties, like we've seen, sort of like a plot. In fact, in MATLAB, it's very much like a plot or a figure, because one of the fundamental properties that actually displays the information is a MATLAB figure. In general, a GUI has what's called an event loop, which it just sits there waiting for a user input as an event or some other type of event to happen. And then an event triggers a callback, which is just a function that gets called. And it executes code on any available properties as we want them to. So basically most of our number crunching and computation is done inside of some sort of callback, which is triggered by an event. And then a well-designed GUI follows what's called MVC, or Model View Controller Design Pattern. And you can have a look at that and look it up if you need to, but it's basically a way to segregate and separate your data from all the other stuff that happens in a GUI. So we'll create a quick little example, shouldn't take more than 10 minutes or so. Follow along if you can, because GUI programming can be a lot of fun, and hopefully this will give you a little intro to it. So in MATLAB, they're created in what's called the app designer. So you just open up app designer by typing it at the command line. That's going to bring up this tool sort of welcome screen. And we're just going to create a blank app. There's plenty of templates here that you can work from. We'll just create a blank app for now. And this is the main app designer window. So first thing is good to do is just save that somewhere and just call it something useful. So Gui Example. Okay, so this is our main canvas that we drop our user interface elements on. That can be resized into something. So this is the size of the base window that we work with. Doesn't really matter. What can be useful is showing the grid, little design grid there. GUI, responsive GUI programming is actually quite tricky. MATLAB does a decent job of providing you with tools and stuff to make it look nice. But yeah, basically we've got this canvas that we then drop user interface elements onto. What we're going to do, we're going to create a simple little plot with some interactive elements, and you can expand on this as you need to. But as I said, we drop in components or user element, interactive user elements onto the canvas from this left-hand side. So you can search. We're just going to start with a axes to drop on, so just our usual MATLAB axes, and we just drag that over and drop it straight onto our canvas here. And you can resize that to some size that is useful for you. And we'll sort of go something like that. We're going to have our main plotting happening here, and we're going to have a few controls down the bottom as well. So got our axes on there. If we click on the axes, down the right-hand side is all the properties of that axis. So just like we were doing programmatic access of the parents and childs and property setting before, these are a way to access some properties of this axis directly. And we can start to see a structure forming over here from the user interface elements here. So our axes is the thing that we just dropped on here. Just double click on this and just call it axes. So this is where you can name what this axis is stored as programmatically. I'm going to drop a numeric field over here and just drop that down the bottom. And actually I might drop down a, is there a label around, or did they get rid of those? Yeah, they got a label here. So I'll drop a label on. And what I'm going to do, I'm just going to give a little description. It's going to plot y equals a sine t 2 by pi by f by t plus phi plus d. So this is what I'm going to do when I actually do the plot, just so we've got a little bit of context. And so that's just a label, and then what I'm going to do, I'm going to allow the user to specify the values of a. We can shrink these to a nice size so it looks reasonable. Okay, so a edit field is the name of this one. I could rename that to something else if I wanted to. That's decent enough though. I can just copy and paste these once I've got my sizing. My next parameter that I'm going to give the user the ability to edit is going to be f. So create all my user interface elements first. The next one is going to be phi, so my phase. And then I'm going to have D at the end here, so they can change those. And then finally, I'm going to have a button which actually does the plotting. So where is my button? I'm just going to take a button here and drop that on. And I'm just going to name that button plot. So it describes what I'm doing. So you can just double click to edit the names of these. It should be relatively straightforward. What I do want to do is just set some default values. So if I click on one of these numeric edit fields, down the right hand side we can see the values here, and this is going to set the default value. So when it starts up, I'm going to set the value to be 1, F can be 1 as well, and then phi default can be 0, that's fine. D default 0 can be 0 as well. Perfect. So by default it's going to plot sine of 2 pi t plus 0. Perfect. So this is my base GUI here. Pretty straightforward, and always save every now and then. Now that we've got some design happening, let's flip over into our code view. So up here is our code view, and we click on that. This is the code that runs behind the actual figure. And it can look pretty daunting at first. Most of it's created by default, which is nice. And we actually don't need to touch a lot of it to start with. So up the top we can see some properties. So properties that correspond to app components. This is the stuff that we've actually dragged and dropped into our designer being created. So we've got our axes, we've got the labels, we can see we've got our F edit field, our A edit field, all those fields that we dropped in. There's the labels associated with them, but these are the things that we need to actually be working with. So most importantly, we've got this plot button. So for our design, our event that happens is going to be the user clicks on the plot button, and that's going to trigger the action of the plot showing up on the axes. So to do that, what we can actually do, you can right click on the button and you can see this thing called this callback menu here. And that's going to give you some useful callbacks that you can be automatically defined. So add button pushed function callback. This is going to be, it's going to create us a little area to create a function that gets called whenever our button gets pushed. That's exactly what we want. So we're going to, again, right click on our plot button, go to callbacks, and then go add button pushed function callback, and just click on that. And it's going to take us across to the code view, and we've got our little function stub here ready to go. So what happens when we click that plot button? Well, we need to what we want to happen is plot the value of that function that we're defining into the axes. So first of all, we need a t. Let's just plot it over 0 and 1. So we'll just create a little linspace there of t. Next thing, well, let's sort of jump ahead. Let's go plot t. Well, hang on. We need to give it an axes to plot to first. So how do we access programmatically the axes that we define? Well, it's a if we have a look back at our design view, remember we said the axes is accessed by going app.axes, and that's actually going to return that axes object for us to work with. So I can say plot into app.axes, and you should see a bunch of autocomplete and hints coming up, so that's handy. So app.axes is the axes that we want to do our plot into. X is t, and the y, well, we know that's going to be a times sine of 2 by pi by t by f by t plus phi plus d. So that's essentially what we want to do, but remember we've only got t defined now. We need to access a, f, phi, and d. How do we do that? We can say a equals, and a is just a property of my app. So it's going to be under app dot, we can see we've got some hints here. A edit field is where a is defined, but that's the actual user interface value. I need to go a level deeper And actually the value, the property that we want is value. So we're going to store the value of app.aEditField.value into the variable a, and that's going to give us a, and we just need to do the same things for those other properties. So f equals app.fEditField, so our naming is coming in handy here, dot value, and then phi equals app.phi_editField.value, and last one, d equals app.dEditField.value. So the value that's stored in these edit fields that we defined is going to be then stored into these variables, and then we use these variables to plot the function that we want into the axes that we've defined. So fingers crossed, if we've done everything correctly, this should work sort of nicely. But we need to run it first, so you can run that by clicking on the run button in either the code view or the design view. So if we run that, a new little figure should appear, and it should look pretty familiar because we've just designed it. And nothing's plotted in the axes yet because I haven't actually told it to. But if I hit plot, we should get that plot coming up with these default values nicely as we defined. So if I then go, let's say a equals 2, and I hit plot, we can see, yay, our amplitude is now 2. We can increase our frequency and hit plot, and now our frequency has increased as we decided to. We can change our phase. Let's see if our phase works. It doesn't seem to like pi there, so we'll just have to define that manually. So maybe if we change our phase to be almost half of pi, yep, so around about, we've got a phase shift as expected, and we can shift that up and down using the d value. So then our midpoint has become 5 or -5 or -2 or whatever we want it to be, as defined by these values here. And then basically you build a full GUI roughly like that. You put in user interface elements, drop them onto your canvas, and then code them in using the callbacks and what you want to do. And then obviously MATLAB's pretty smart, so it's auto resizing with the size of that window there, so which is quite nice. That's, yeah, sort of a very quick introduction to programming in GUIs. Probably a bit too quick to be useful, unfortunately, but yeah, maybe a little bit helpful, at least if you're going into it in the future. You won't be starting completely from scratch. And yeah, everything seems to be working pretty much the way that we would expect it to there. Right.
Actually, I feel this is quite interesting to how the GUI interface is created. I'm using MATLAB toolbox, which is written by my supervisor.
Mm-hmm.
That toolbox also has such a GUI interface.
Yeah, yeah.
Now I get a little bit idea how he has written that toolbox.
Yeah, yeah. Do you have access to the source code of it, or has it been sort of locked away from you?
It's open source.
Yeah, yeah.
Because I'm not that good at MATLAB, so I don't know how he has created. It seems interesting.
Yeah, it can be quite interesting. The difference is, if depending on how long ago it was written, MATLAB has recently changed the whole way that this GUI designer works. It used to be called Guide, G-U-I-D, which I'm not sure whether you can still access. No, I don't think so. But they've renamed it to this app designer thing, which is a lot better. The old way used to be very bad. I didn't like it. So this way's a little bit nicer, and it really sort of gets your you know, if you're looking at this code, something like this code here, you really want to be up on object-oriented programming, which is, you know, the way that this sort of works. It's all based on objects and where those objects are stored and properties like public methods and private methods and things like that. So it can be a little bit daunting, but at its core, yeah, we're working with an event loop and callbacks. So, you know, if you're chasing through that GUI that you've been provided with, you'd find, you know, what are the callbacks that have been assigned to certain user interface elements. So a button's pretty clear, right? When you click on a button, that's my event that's happening. It's that button click. But alternatively, we could set the callback from value changed, right? From one of these edit fields. So instead of me having to click the button, when I change that value, now I could trigger a different function from here. So I should just be able to call plot button pushed and give it app. Nothing. If I do that, I believe, if I've done it correctly, in fact, I think I can pass event through to be a bit clearer. What it's going to do, when I change this value, I don't even need this line now. When I change this value, it's going to call the button function. It's going to call the button callback. So instead of me, the user, actually having to press the button, now it's this other callback that then acts to push the button for me. And it's going to do the same thing as pushing that button. So if I run that, let's see what happens. So if I change the value of A now, it should update my plot automatically. Yeah, so that's doing that now. I change the value, I press enter, and you can see it's changing the scale. It doesn't look like much is changing. But now when I change that value, it's basically doing the job of pressing that plot button for me. So we don't even really need that plot button if you set this up nicely. If I do it on the F, for example, it doesn't change it when I press enter because I haven't defined that callback that changes when I edit the value. I've only done it for the A. So if you're smart about it, you can knock off a few different things in one, but that was done by, yeah, just changing the callback for a particular user interface element. In that case, it was the edit field. And yeah. Takes a bit of practice to get used to, for sure.
Actually, I just a bit lost after you called the app designer, and then how did you open the canvas?
Yep, so you create a blank, let me start again. I'll just close that out. I'll start from scratch because of app designer. So that opens this for me, and then if we create a blank app, it opens up this canvas, and then you can start dropping on the user interface elements onto there directly. So we had axes, and we had a button, and we had the numeric fields. Yeah, just dropped onto there, and then changing the callbacks and stuff. And yeah, you can see all the callbacks by click on that callback, I think. Yeah, probably don't get into that. There's a lot of stuff to explore there. Great.
And are these field axes are the children of the
Yeah, so they're children of this. Everything is a child of this variable that we've called app, which is sort of this. That's this broad level class or object here is called this app, and that's appearing like this. And then it's got properties, which is sort of think of like children. It's got properties of, in this case, a figure and axes and the buttons and stuff. They all live within this thing called app. So all the stuff that you program on, all of your user defined things are going to appear, be able to access by app dot something. And we can see these sort of being in our create components, the auto-generated one, you can see all the work that MATLAB is doing behind the scenes to create all the different UI elements that we've defined. Luckily, MATLAB is pretty smart and it does it all automatically for us without having to do much work. And yeah, the main things that we need to worry about is defining the callbacks for those particular ones.
Really good to know. Thanks a lot.
No worries at all. And yeah, that's pretty much the end of what I've got. So it's good timing, I think, a little bit over 2 hours. Yeah, I'll have to refine it a little bit for the future workshops, but hopefully it was somewhat useful. And yeah, any feedback is much appreciated. There's just you at the moment, so yeah.
It's really a helpful workshop and learn many tricks. Because I use MATLAB, but it seems my code that not that efficient. Or I have some bad habits.
Yep.
And then it's good to see how you programming and then improve the code efficiency.
Yeah.
Time,
The timing information is quite useful if you're running, big models. What sort of stuff are you programming? Are you doing like large models for? Oop, dropped out. Sorry, dropped out there.
no worries.
Yeah, you're doing like large modeling type stuff for environmental, projects and things.
So I study the impact of climate change on groundwater,
Mm-hmm.
and then my supervisor has created a groundwater analysis toolbox using MATLAB,
Yep.
and I basically use that tool
Oh yeah. Okay.
to analyze the groundwater level changes, and then it takes the climate data like precipitation, temperature, evapotranspiration.
Okay. Yep. Gotcha. So that the GUI itself is doing most of the heavy lifting in terms of the computation, or do you do some computation as well?
The GUI is the groundwater model, so I give the input data and get the output.
Mm-hmm.
But actually, I have a lot of groundwater data, so I need to analyze all the groundwater balls in Australia.
Yep.
And I upload the models to HPC, and then it can run there. But actually, I'm also a little bit confused how to upload the MATLAB toolbox to HPC.
Right.
My model run there.
Mm-hmm.
But luckily, it's an invited function that my supervisor also designed that function in the code, so I can also use it directly.
Nice. Yeah.
He's really a very good programmer.
Excellent. That's good. That's good. Well, yeah, hopefully it was a bit of help. And yeah, if you need to review anything, I've hopefully got the recording sorted out, and they'll be going up onto the MUEC YouTube channel, so you can have a look and review anything that moved too quickly or whatever. But yeah, hopefully it was a bit of help, and thanks so much for coming along. It was, yeah, we had two in the first half and one in the second half, and I'll need to figure out a way to promote these more or get people to turn up, because there was, yeah, as I said, there was so many people on the Facebook interested, but
Maybe you can put it on the student notice board.
yeah, it's a good idea. I think
It's really nice and useful. I find it very good and high quality.
excellent. Good to know. Thanks so much. Yeah, so we've got some more workshops running. Next week is an off week, so there's nothing next week, and we're just finalizing the schedule. For the next few weeks, but there's a few other things. So I'm doing a LaTeX workshop, and then I've got a Git workshop later on. I think we're doing a CAD workshop. So yeah, a few things to come, but next week is an off week, so nothing next week.
Great. Do you also have a YouTube channel? Is it also MECC?
Yeah, it's in that text channel. If you just scroll up in the text channel a bit, I think someone posted the link a couple of times in that. So
I can click on
Yeah.
kind of do.
Perfect.
Great.
All right. Well, I better go. I'm starving for some dinner, so.
Me too.
Yeah. All right. Thanks for joining. I'll catch you next time.
Thanks a lot. Bye.
Bye. Hey, Jeff. Good. Oh, that's all good. Yeah, it went well, I think.